Bashore. Ben is an old friend of my son's. We've known him for many, many years. He lives in Claymont. He's a Claymont native. He received his bachelor's degree in geological sciences from the University of Delaware in 2021 and is currently working on his master's degree at the University of Delaware, focusing on geochemistry. Though geology is a wide field, Ben is particularly fascinated by earth materials and their origins. He's always been a bit of a rock collector. Brought some with him, as a matter of fact, but found his passion for geology late in life when he decided to go back to school around the age 25. Since starting his graduate studies, he's been fortunate enough to assistant teach TA for a wide range of undergraduate lab sections, including Geology 202, which is earth materials, which is what his interest really is. It also focuses or does focus on mineralogy. Ben has traveled extensively for his geological studies, spending a total of 7 weeks in the Western United States, participating in field programs. He will discuss his current research also and touch on the laboratory equipment they use and why they use it, as well as current findings and how it might be used in the future. So I welcome Ben Bashore.
Thank you very much. All right. So, hello. Yes. So I'm Ben. And so I tried to keep this talk. I wanted to talk a little bit about my research, but I also know this is an eclectic audience. It's just kind of generally interested in what I do and a little bit of geology. So keeping it general interest, but during the second half of the talk, we'll probably dive into some pretty nitty-gritty science stuff. So if there's any questions, like they said during the talk, feel free to raise your hand and chime in and tell me you're confused, because that's okay. So let's get this ball rolling. I think Alan just mentioned most of the stuff right here. This is me. This is one of my favorite pictures that have been taken at the Grand Canyon of myself. So one of the things I was fortunate enough to do in my undergraduate degree is that you have to go on field programs to get a degree in geology. And I was lucky enough to spend a lot of time out west looking at the really cool rocks and formations that are out there. And this is one of my favorite locales that I've been to. So I had to put this picture up in the beginning of the talk. And one other thing that I also do is I work at the Delaware Museum of Nature and Science, as well as TAing at the University of Delaware. If you guys have never been to the Museum of Nature and Science, it's a really wonderful place. Cannot recommend it enough. I had to plug it here. But I love my job. And for the most part, I don't tend to do this as much. I tend to do more informal education. But I thought this would be really fun to come out here and tell you guys a little bit about what I do and geology, and get you guys hopefully thinking of some interesting questions to ask me. But yeah, most of the time I'm doing that, giving tours to first graders. So this is a little bit of a change of pace for me. So I guess just to start, let's start with the bare bones basics, right? What is geology? I think most people have kind of an idea of what geology is. They probably involve somebody in a tan vest with lots of pockets, smashing open rocks in the middle of the desert with a big hammer, right? And that's not entirely untrue. There's definitely some people that do that. If we break down the word, like we're wont to do with definitions, so geo means earth, right? If you think of geometry, it has the same root word, which means the measurement of the earth. Geology is the study of the earth, which, in my opinion, is a little bit of a broad topic. So let's try and break it down even further and look at some of the things that geologists do study. So I think a better definition of geology is it's the study of the earth, its materials, and the processes which shape it, both those materials and the earth itself. There's a lot going on there. It's still pretty broad, but we're starting to focus in on what geologists might study. And though I focus on mineralogy, pretty much all areas of geology interest me. So one of the things around here that you might see people studying a lot is coastal environments. So we live on the East Coast. There's a lot of interesting things that happen on beaches. And I like to take pictures of geological stuff wherever I go and I travel. So that bottom picture right up there is actually Shizuoka in Japan. It's a cobblestone beach that has lots of black sand because that's a volcanic area, right? So basalt is which is one of the rocks that I have right here, is pretty dark. And so when you get different kinds of rocks and different kinds of coastal environments, you're going to get different kinds of beaches, right? There's people that study the shifting and the way that beaches move from tides, people that study waves and that impact on beaches. So there's lots of people that do things like that on the East Coast. Glaciers is one thing that a lot of people might not think of geologists as being someone who studies glaciers, but we absolutely do. One of my professors during my undergrad did his PhD in glacier studies. Glaciers are kind of like rivers. They're just slightly slower moving than most rivers, right? That picture up there is me on a glacier in Iceland, which is a wonderful place to see glaciers if you ever have the fortune to be up there. River systems is another big one. So geologists study rivers. Whenever I fly in a plane, I tend to look out the passenger window and try and take all the pictures of the really pretty. I love meandering stream systems like this one in the photograph right there that just kind of wind back and forth. So studying how geomorphology, fluvial geomorphology would be studying how rivers form, how they shift over time, how they erode, how they deposit material. Volcanoes might be an obvious one that people know, but geologists are going to study liquid rocks, not just breaking over old solid rocks. Fossils, again, a big one. Paleontology is a discipline of geology. And then two that people might not think of a lot, but are super important, are soil sciences and hydrogeology, so looking at groundwater and soil. So anything from constructing buildings, if you need to know what the subsurface looks like, from agriculture, looking at groundwater and the soil quality, all the way up through things like Superfund projects, where you're cleaning up spills and old industrial areas that have lots of pollution. One important question that people might ask is, well, if this groundwater is full of toxic chemicals, how do we get that out? And how do we stop those chemicals from moving to other sources of water, right? So those are hydrogeologists and geochemists that do that. And just to kind of hammer home the point of how multidisciplinary geology can be, this is one of my professors. He was one of my professors during my undergraduate, as well as my advisor. His name is Dr. John Madsen. And we like to call him the geophysicist. So he's a geophysicist, which means that he's trained to use equipment such as sonar, radar, LiDAR systems, seismometers, and he uses those pieces of equipment to study usually waves, different kinds of waves, sound waves mostly, to study things like the interior of the Earth. He could put that on a boat and look at the subsurface of the ocean or a lake bed or a river bottom. What he actually does for his research is he looks at Atlantic sturgeon populations in the Hudson River and tracks them. So he has this boat right here that tugs on a piece of equipment called a side scanning sonar behind it. It's essentially kind of like almost looks like a big long barracuda, and it sends sound waves out to the side of the boat, hence the side scanning sonar. And when these sound waves hit something like the bottom of the river, they're going to bounce back. There's a receiver on that instrument, and based on the reflections that you get, the speed they come back and the way they're reflected, you can get a pretty good image of what the bottom of a riverbed looks like. And depending on the system, you might even get information on what the subsurface of that riverbed looks like. But what he's looking at is if you see those little yellow lines, yellow or orange lines. I'm colorblind, so if I say weird colors during this, that's why. But those lines there, those bright lines, are actually fish. Those are fish that when that sound wave's going through the water, before it hits that the river bottom, hitting that fish first and bouncing back. And you get this brighter signal because it's bouncing back quicker. It's hitting that fish in the water column. And because it's hitting that fish before it hits the bottom, it doesn't ever reach the river bottom. So you get this shadow right underneath the fish. So we'll take this along the Hudson River. He scans, he looks at sturgeon populations, and he tries to find how many they are and where they're nesting. Because sturgeon some species of sturgeon are threatened. We use them for caviar, they're fished, sometimes overfished, and we also tend to disturb their nesting sites. So it turns out they tend to nest and lay their eggs in like rocky outcrops and things like that, where if we're dredging or doing construction, we can disrupt that. So that's one of the things that he does for his research. So it's not just breaking open rocks. We also look at fish and rivers and glaciers and all kinds of stuff like that. So one of the things that fascinates me, and one thing that's gonna sort of drive us into the rest of our talk is the history of geology, which I thought I'd do. I mean, I could probably do an entire slideshow on this. I did three slides instead. There's a lot to it. And one of the places I like to start just to show that geology, as long as there's been interesting rocks and things on the ground, people have been writing about them. And so one of the guys I like to point to is this gentleman up on the left here, which is Pliny the Elder. So Pliny the Elder he was born in 23 to 24 AD. They're not sure. And he was kind of a multidisciplinary guy. He was a physician, he was a philosopher, he was a writer, and he was also what they might call in the 1800s a naturalist, right? A natural scientist. And one of the things he's famous for is creating the first known encyclopedia. So instead of just writing down what he thought, he made his own observations, yes, but he would go take other people's writings, other people's books, and compile them into volumes for other people to reference. And as far as I know, that's the first guy that we know that did something like that. And one of his books, one of his volumes was called Historia Naturalis, or Natural History, in which he talks about everything nature that you could possibly know in the ancient world, much of which was geology-based. So, for example, he was one of the first people to realize what amber was. He realized that amber was, in fact, fossilized, he wouldn't have used that word, but fossilized tree sap. So he noticed that insects, when tree sap is coming down the tree, insects will crawl up to it to try and get a nibble. They'll get covered in it. The sap hardens and it falls off the tree. And he realized that the stuff he was finding in the ground, some of it even smells still like tree resin. This stuff was ancient tree sap with bugs in it, right? To him, ancient would have probably been hundreds to thousands of years instead of millions, right? But it's a step in that right direction to get to where we're going today in geology. And if you need any more proof that Pliny was really into rocks, that mountain down there in that picture is Mount Vesuvius. So Mount Vesuvius in Italy erupted, and it erupted in 79 AD. So if you're paying attention to the slide, that is also the year that Pliny the Elder died. So the story goes, he was on a boat with his nephew, and why he went to shore is up for debate. There's multiple stories around this. Some people say that he went just to get a closer look at the eruption. Other people said he was going to shore to try and save people, citizens from Pompeii and Herculaneum. Either way, he went to get a closer look, and he didn't make it back out. So he died doing what he loved, which was looking at really interesting geology. Another really interesting tidbit I wanted to talk about, fossils are pretty common knowledge now. Everybody's heard of dinosaurs. Everybody knows that animals have gone extinct. But that is something we take for granted. In anything prior to the 1700s, extinction wasn't even really in our lexicon. We didn't understand that animals just don't exist anymore. They all die out. We didn't think that could happen. So when ancient people would find fossils, they couldn't quite explain it, and they would come up with other stories to explain what they found. And one of my favorite examples is these snake stones. So there's lots of legends in Europe of saints or other figures turning snakes into stone. And when people would find these fossils of what are known as ammonites, which are actually ancient squid-like creatures that would have little tentacles coming out of the end, right? They thought that what they were finding was coiled up petrified snakes. And so people would take these materials and they would carve little snake heads in them and sell them. And I've actually brought one from my collection today if people want to take a look at the end of the lecture, because I think this is a really interesting part of kind of intersection between mythology and geology that's really neat. But if we fast forward a little bit to sort of more scientific age, if you look into the history of geology, chances are one of the first names you're going to see is this guy, James Hutton. He's known as the grandfather of modern geology. And one of the things he's famous for, among many other things, is this rock formation right here that I've put up. So this is known as Hutton's Unconformity. It's Syccar Point in Scotland, which is where he was from. And in the 1700s, James Hutton goes to this point. It's kind of like the Newton's apple of geology. And he sees these rocks. He notices that these rocks are made of materials that we can find in sediment. They're made of sand, they're made of mud, they're made of silt and clay. They're just compacted and hardened over time. And he notices that this one layer on the bottom is kind of lined up like this. The layers are stacked like they're on a bookcase. But he also noticed, and this is a term known as law of original horizontality, which just means that when mud and sand is deposited in lakes and oceans, they're always deposited horizontally in flat horizontal layers like this, because that's just how gravity works, right? So he figured, okay, something must have happened to these rocks where they got deposited. Enough time passed that they became hardened and lithified and became rocks. They got tilted, eroded, and then another layer of rock was deposited over top of that. And then that was hardened and that was tilted. And his aha moment was like, this would have taken a really, really long time to happen. So if we're thinking back to the 1700s, this is before Darwin. This is at a time when most people, if you ask them, they would have told you the Earth is about 6,000 years old. And Hutton realized it must be much, much older than that. These processes must take a long time. But he also realized, and there's a quote that's attributed to Hutton, which is the present is the key to the past. It's a bit apocryphal, but it's the general idea of what he wrote down, right? So that means two things. One, that the rocks that we find in the present, we can look at those materials and interpret something that happened millions of years ago from that information. And what it also means is that the processes that are happening now on Earth have always happened, and we can look at those processes to inform us of what might have been happening in ancient history here on Earth, right? And for the most part, there's always been some back and forth between that. Some people called catastrophists said, no. Everything's pretty blasé for most of Earth's history, and then these crazy catastrophes happen, and that's how we get all these rocks and formations. You went back and forth on that for a while, which does happen. But for the most part, this is correct. We can interpret what happened in the Earth's past based on what we're seeing in the processes today. Fast forward a little further to the 1900s, we get this guy, Alfred Wegener. So Alfred Wegener is hugely important to the history of geology because he's one of the first contributors to what we would probably call our foundational theory in geology, which is plate tectonics. Alfred Wegener was actually a meteorologist. He was not a geologist, but he was kind of a Renaissance man. He was interested in all facets of science. And one of the things he noticed is something that probably a lot of people notice. When I was at dinner with Alan, I think you guys said exactly this, which is that if you look at a map of the world, it looks pretty darn sure like South America should fit right into Africa, just slot right in there, right? And I remember being in grade school and thinking that exact same thing. And he saw that, and he had a moment where he thought this too. And he starts to do some research. He finds that not only is that the case here, but many other landforms in the world seem to have this quality. And if you look at the rocks and fossils on these land masses, they seem to match up like a puzzle. So the fossils that you would find in West Africa are pretty much identical time period and species to the fossils you're going to find in places like South America. If you look at the rocks that compose the Appalachian Mountains, same exact age and types of rocks you find in the Scottish Highlands all the way across the ocean. And this is the case throughout the entire world. Alfred Wegener started looking into this, and in 1912, he publishes a paper and he proposes this theory called continental drift, that the continents were once all connected, and they slowly have drifted apart over time. He was laughed at, right? People did not take him seriously. First of all, he was a meteorologist. What does he know about rocks and continents? And he also couldn't provide a mechanism for why that would have happened. As far as Alfred Wegener could tell, he thought that the continents just kind of plowed through the ocean crust very slowly. But he couldn't provide any other evidence than that. So he was pretty much a laughingstock. He was a pariah. He didn't appear to let it bother him. From all accounts, he just continued on with his work and was completely happy till the day he died in 1930. He was 50 years old. He died out in Greenland doing studies on meteorology. But he was not too shortly after that to be kind of vindicated. So in the 1940s, we had a lot of developments in instruments that would become pretty integral to geophysics, sonar being one of them. And people like Henry Hess, he was a naval officer in World War II, in his spare time when he was out in the ocean, he would point his sonar down to get readings of the ocean floor. And one of the things he noticed was that there was mountain ranges on the ocean floor. Up until that point, people had assumed that the bottom of the ocean was just flat mud. but it's not. There's mountain ranges, huge mountain ranges, and volcanoes under there. And in the 1950s, two people, Marie Tharp and Bruce Heezen, ended up taking expeditions around the world and mapping the entirety of the ocean basins. And this is a painting that was made later on. It was made in the 60s. This is a painting that represents all of their data that they collected and what the bottom of the ocean looks like. And it's pretty stunning. You see these suture points, these huge mountain ranges that encompass the entirety of the ocean basins. And people ended up realizing what these are giant volcanic mountain ranges where the earth is literally splitting apart and the oceans are drifting away from each other. And this is mostly the evidence that we have even today that tectonic activities happening and plate tectonics happens, right? There's a few other things, magnetic data. People took data in places like Greenland, ironically enough, and other continents around the world where it turns out the magnetic poles, you can get magnetic minerals that align with the magnetic poles. And when you take these ancient rocks and you put them in an instrument that tells you where the North Pole should be, they don't point to the North Pole. Because when that continent was where it was when those rocks formed, it was pointing to the North Pole, and then it moved. And that data is consistent throughout the entire world. So the mechanism that Wegener never understood was this right here. So in the Earth's mantle, so we have the crust on the outside of the Earth, we have the mantle, and then we have the core. And a lot of people think of the mantle, especially little kids that ask me about geology, they think that the entire Earth is just a big thing of lava down there. It's definitely not. It's almost entirely solid rock. And that's because even though it's hot, it's under a lot of pressure. But it doesn't behave like we would imagine solid rock to behave. It behaves almost like a putty. So it is malleable, it moves. And over millions of years, we get what are known as convection currents. So just like if you think of a lava lamp, we get the heat from the bottom, heats up that wax, floats, cools down, and then sinks in a cycle. And these convection currents, if you look at those arrows, are happening in the mantle. And they happen in different areas. And when they're moving apart from each other, that pushes the crust away kind of like a conveyor belt. And as far as we know, and this is still an area of active study, but as far as we know, this is the mechanism by which plate tectonics happens. And so the materials that are involved here are, for the most part, basalt and a rock called peridotite, which is one of my favorite rocks. So basalt, most of the ocean crust, continents are really complicated and messy, but oceans are not. Oceans are nice and clean, and I love them. The oceanic crust is pretty much entirely made of basalt, which is the dark gray rock that's in here. If you think of like the Hawaiian Islands, those are made of basaltic rocks, right? Very dark typically. And it's also very dense. So when that dense ocean crust hits a continent, it's going to sink underneath of it, and it's going to do what's called subduction. It's going to go underneath of that other plate, remelt, and get recycled again in this big rock cycle. The mantle material, this is why I brought this rock here, is made of this rock called peridotite. It's made entirely almost of olivine, which some pyroxene. Olivine, if you're familiar with peridot or peridot in the gemstone variety, that's what gemstone quality olivine is. And this rock that I brought here today is actual mantle material that came up through volcanic eruption. So if you want to take a look at that later, I'm going to keep these all up here as well. But this reminds me of just one of the beautiful things about geology is that if you dig down into the earth, the majority of the mantle is just this beautiful green crystalline rock, and I think that's really, really fascinating. Oh, and those are some basalt columns in that picture back there as well, which is one of the coolest rock formations in my opinion. That one is actually in Iceland. I didn't take that exact picture. I also noticed this morning that there was a watermark on there that I forgot to remove. But I was at that location when I was in Iceland, and it's a really, really beautiful example of basalt columns. Yeah. Yes. Yes. This one? So this is from Arizona is where they got it. I bought this at a rock show. Yeah. Oh, so the mantle. So that stuff that's labeled mantle is where that rock comes from. Normally it's too far underground to get to it. So we didn't. Nature brought it to us. So every once in a while, if you get volcanic eruptions that start really, really deep underground, they can start in the mantle. And if we're lucky, they will bring chunks of the mantle up with them. So they're called xenoliths, and sometimes they're found in volcanic rocks. Yeah, that's a very good question. Yeah, we have up and as far as I know, we have not drilled into the mantle. We've never done that. It's too deep and it gets too hot. So yes. Yeah, the Moho. Yeah, yeah, yeah. They did stop it. Yeah. So he's asking about it was I think it was called Project Mohole. Project Mohole. Yes. Yep. So it was a project where they tried to drill down to the mantle, and I think they tried to do it pretty close to a coastal area, or maybe in the ocean. I don't remember. But they didn't get there. So when you get that deep, so ocean crust is something like 11 kilometers deep or so. Continental crust is about 70. And when you get down to like just 7 or 8 miles, the heat down there starts to just make those drills not work. It gunks them up. The rock doesn't behave brittly anymore. So it's almost like you're drilling through taffy. So we have not done it yet. We've never gotten there. There's a project right now. I think there's a Japanese research organization that's trying to do that with boats. Oh yeah, so he's asking if they could use something other than a traditional, like a typical drilling rig. And I don't know the answer to that. I don't know what they would use. Yeah. Similar, I think the one that they're doing right now in the ocean drilling is similar to what they do for oil rigs and things like that. So, yeah. No, yeah, good question. Yes. Well, because I suppose just to find out what's down there. Yeah, we want to know. No, there could be practical applications to that, but I don't know off the top of my head if there are any. But I know I personally want them to because I think that's neat. But yeah. I guess just on that topic, this is a good segue to start talking about earth materials and minerals, right? So olivine is a mineral. It's a crystal. So what do we mean when we say mineral, right? It's not just something on the backs of our cereal boxes, right? They're talking about something different. For a geologist, when we talk about a mineral, what we mean is something that fits these criteria. So if you look into a geology textbook, this is going to be the things that they list that tell us that this object is or is not a mineral. There's two of these, which is the top two, that are a little contentious, which is that it's naturally occurring, so it can't be man-made, right? Some people would find that a little contentious because if you make a lab-grown diamond and then you take it and you put it next to a naturally grown diamond, they're exactly the same thing. In fact, the lab-grown diamond is more pure than the natural one even. So, take that with a grain of salt. No pun intended. Also has to be inorganic, right? So not biogenic in origin. Again, there's minerals in our teeth and our bones. Seashells use the mineral aragonite, right, for their structure. But if you're taking the textbook definition, we don't count those as minerals. We count them as biogenic stuff. But the last three are pretty unequivocal. So it's got to be solid at Earth's surface temperatures, right? So liquids aren't crystalline. They can't be crystals. So no liquids are minerals. But if it's solid, then it can be. It has to be crystalline, so its atoms have to be arranged in a certain way. And next slide, we'll talk a little bit more about that. And it has to have a definite chemical composition, right? So if we take salt as the example, salt is sodium chloride. It's nothing but sodium chloride unless you got impurities in it. And you get salt crystals, right? So it's a single chemical composition throughout the entire substance. And so one of the fun things about science when we start to, humans love categorizing things, right? And sometimes when we do that, nature throws us a little curveball and something unintuitive that we don't typically think of as being in that category. But if we follow it to the letter, it ends up being. And so one of the materials that actually falls under all of these categories is ice, which it is, right? So it's naturally occurring. Nobody would argue that. It is inorganic. I don't, maybe there's animals that make ice, but I don't know about them. It is solid at Earth's surface temperatures. In fact, there's places on the Earth where it's always frozen, right? So that's called a glacier, right? It is indeed crystalline. If you just look at those pictures, that's enough proof for that. It has a definite composition, right? It is H2O. It's two hydrogens and an oxygen. So if we take this a little step further, that means that So the definition of a rock is just a collection of minerals, right, in a big clump. So big sheets of ice, that's a rock. Do we have a name for liquid rock? Does anybody know what the name is for liquid rock? It's lava. Yeah, that lava or magma, right? So which means that water is lava. So if we take that one step further, we're made of 70% water, which means that we're lava monsters, right? So that's that's not my original joke. That's somebody else, but I really like it as an anecdote, right? So delving into crystals more, because this is starting to get into more what I research and what I'm interested in. What do we mean by crystalline, right? So we're using salt as the example again here, right? It's sodium chloride. And when we say something's crystalline, what we're really saying is that their atoms are arranged in a particular order. So if you look at that picture of the atomic structure of salt, it's got a sodium, a chlorine, a sodium, a chlorine, a sodium, a chlorine, a sodium, chlorine, over and over and over and over and over again in this crystal lattice is what we would call it. And that typically is also expressed in the macroscopic way that crystal grows. So that crystal lattice is cubic. Salt crystals are also cubic. That's the way they have to grow because of their atomic structure. Also, yeah, I could have put regular salt in here, but I think blue and purple salt is way more interesting and pretty. So I would like that on my pretzel personally. But yeah, so that's the definition of a crystal. And if you can have substances that are not crystalline, right? So another good way to look at this is this little picture over here. So we have crystalline things that are lined up perfectly. Their atoms are nice and ordered. We can have amorphous substances as well, where their atoms are not ordered at all. So the difference, what does that look like? Up at the top there, we have a mineral called quartz. Quartz is silicon dioxide, is the chemical formula. And it is a crystal. Its atoms are arranged in a particular structure. And if you look at it, a crystal of quartz is very geometric. It has a pattern not only in the atoms, but also in the macroscopic structure. Below it is a piece of obsidian. So obsidian is volcanic glass. It is also silicon dioxide. Yes. Yeah. Oh, great. So, okay, that's a really good question, actually. So, she said, why, if one of the definitions of a mineral is that it's a definite chemical composition, why is some of it purple and some of it not? Excellent question. So nature is never as simple as we want it to be. And pretty much any naturally occurring mineral is going to have impurities in it, right? So the majority of the structure there is sodium and chlorine, but you might have some lithium that sneaks its way in there. You might have some magnesium or what have you that gets in its structure. So it's not pure is why that is. So lab-grown salt would probably be clear or white, depending on how fine the grains are. But yeah, so most coloration in minerals, so things like, you're probably all familiar with amethyst, right? So amethyst is simply purple quartz, and that is due to, I believe it's chromium that's in amethyst that does that, right? So it's just little tiny impurities of other elements that get in there. Or sometimes for rose quartz, I believe it's air bubbles that get in there milky quartz. It's air bubbles that get in there that make that milky color, right? So good question. But yeah, so this obsidian here is what an amorphous version of that exact same chemical composition looks like when we don't have a crystal structure, right? So it can make very different objects with different properties. So now we're going to start to get into my area of research, which is gypsum. So I study the mineral gypsum. I study how gypsum grows. And gypsum, I have a very big piece of gypsum right here. This is a piece of satin spar gypsum. Gypsum is calcium sulfate dihydrate is its chemical formula. You can get, oh yeah, thank you, Alan. Yeah, ooh, yes. So gypsum can take a lot of different forms. So there's desert roses up there that some people might be familiar with in like rock shops and stuff. Sometimes those are made of barite too, so they're not always gypsum, but they can be. We have satin spar gypsum like this. Sometimes we have selenite, which is nice clear pieces of gypsum. But the place that you guys are probably most familiar with gypsum is in drywall. So gypsum is used they make a slurry of gypsum, they pour it into a mold. When it dries, they put it up on the wall. It's nice. It's basically a plaster, right? So that other picture that we saw, that is a very simple crystal lattice. Salt is about as simple as you can get. Gypsum, as you can see in that picture, is not so simple. It's got a lot going on there because there's a lot more atoms involved, and its structure is much larger. So these are what we arranged in what we would call a unit cell. So a unit cell for a mineral is the smallest number of atoms you can get in a space that translates to the entire symmetry of the crystal. So you could take one of these and just repeat it over and over and over and over and over again, and you get the exact same thing. And you can kind of see it's got this rectangular structure. And if you look at the one that I brought today, you can kind of see how that might stack up in these fibrous like columns, right? So it translates to the larger structure of the mineral. And you can even get things known as cleavage planes. So these are one of my favorite things to talk about. They confuse Geology 107 students all the time, but it's very important to learn. So I've brought a crystal of calcite here. Oftentimes crystals, when they form, like this quartz, that wasn't cut by anyone. That's just how that crystal grows. This is not how this crystal grew. This probably looked a lot more similar to that pointed tip of quartz. This is how the crystal breaks. So if you smash this with a hammer, it's going to keep breaking into smaller and smaller and smaller rhombuses because of its crystal structure, right? So the weak points in the atoms, where those atoms are connecting in here, they're always going to break along those weak points, and sometimes you get these perfect flat breakages called cleavage planes. So the atomic structure is really important for the macroscopic properties of minerals, just like this, or like our gypsum here, or the way they grow, which is really cool. And this is a little bit of a segue. I just think this picture is really cool. This is also gypsum. So this is, and those are real humans that are in there. This is a cave in Chihuahua, Mexico. It's called the Cave of Crystals, fittingly enough. Those are huge selenite crystals. And what my research is doing is I am looking at how gypsum grows from, or goes from a solution dissolved in water to a solid crystal. How does that happen? How long does it take that to happen? How fast does it grow once it starts happening? These crystals, this cavern was completely submerged in water before miners pumped it all out. They did not know that this chamber was here until they pumped that water out. When they went in, that's what they found. So these crystals are enormous. I think the numbers I saw for that really big, some of the largest ones in there are something along the lines of like 7, 8, 9 meters long, might even be longer. That one probably looks like it's longer than that. Huge crystals of selenite gypsum. And these probably took, by the best estimates we have, millions of years to grow like that. That cave was submerged underwater for millions of years in the perfect conditions for that gypsum to grow. And one of the things that fascinates me and other geochemists and people who study mineralogy is exactly that, the conditions in which a mineral is going to do that, why it does that, how big can they get, how long does it take them to get that big. So how do I and other geologists study that? So this is the instrument that we use. We use a technique called atomic force microscopy. So that may not look like it, but that is a microscope that we use. I think it looks a little bit more like a microwave. But once you open it up, it looks a little more sciencey on the inside. That small little circle in there is the stage where we would put our sample. And this is a particularly expensive piece of equipment. It's very, very sensitive. And we can use it by inserting these little probes. So rather than using a light microscope, which is going to shine light through or on a subject to get a better look at it, we aren't using light or cameras at all other than to position our probe over top of our sample. We are using these tiny little probes. And I actually have, I've brought some here today. These are old used ones. But you might not even be able to see them in there, but you can take a closer look later on in the talk if you'd like, or after the talk if you'd like to. But they're very small silicon nitride probes. And at the end of, so that is a picture that I took last week in one of the light microscopes in my lab of the probe. And you can see those tiny little triangular tips on the end there. And at the end of each one of these tiny little tips is another tiny little tip that comes off of the end of it, right? So it's tips on tips. And that tip is almost atomically thick at the end. It's very, very, very sharp. And what we use this to do is rather than looking at an object, we scan it. So it's called an atomic force microscope. And the atomic force we're talking about is when we get objects very, very close to each other, atoms close to each other, they never actually quite touch. There's a repelling force there, right? And so our tip, as you can see in that little picture, is coming directly up to whatever material we're trying to look at. And it's going to scan along the topography of that surface. We have a laser that shines off of the cantilever, right? So the part that little, if I'll go back to this other picture, whoop. Right, so that triangular bit is the cantilever, the tip comes off of that. So that cantilever has a reflective surface, a laser reflects off of that, and if that tip's going along and it hits a bump and it goes up, it's gonna deflect that laser. And it has a photodiode there that is very, very sensitive and can detect how much that laser was deflected by. And when we run this over top of a surface over and over and over and over again, it goes actually quite fast because it's so small, we get images like this. So this is not a light image, this is a scanned image. And this is the surface of a mineral. I believe this is scheelite, but I'm not 100% sure because my memory fails me. But the scale we're working at is 1 micron. So that white bar there is a single micron, which is, there's 25,400 of those in a single inch. So we're talking very, very small scales that this microscope can work on. In the right conditions, this microscope can actually resolve atomic resolutions. We can see individual atomic bonds with this microscope. It's pretty amazing. So what are some of the applications of the AFM and why was it invented? So the AFM was invented in the 80s, the early 1980s by IBM. So IBM initially developed these, as far as I know, to look at computer chips. So that first image up there is a silicon chip. So that is the structure on a silicon chip. And as far as I know, that's why they first invented these things, to look at those. You can also look at biological things. So that is an image that was scanned of a Golgi apparatus. That is one of the organelles that are inside cells. And then this picture over here is a picture of graphene. So if you're not familiar, graphene is just a sheet of carbon, and it is what graphite is made of. So the stuff in your pencil is just a bunch of sheets of graphene stacked on top of each other. And when you write with it, it just slaws off layers at a time onto the paper, right? So graphene is made up of a bunch of carbon atoms arranged in a hexagon, all connected to, to each other in a big sheet. And so this is actually, we're not looking at the atoms themselves. What we're probably seeing here is the bonds between atoms, but that is atomic resolution. That is the atomic structure. That is a picture of the atomic structure of graphene. So that is one of the things that you can do with this microscope. For geology, what we tend to use this for in mineralogy is we look at mineral surfaces. So we're able to resolve the surface of a mineral in real time very, very accurately at very small scales. So these images up here are images of the surface of calcite. Some of them are probably in dry air, but most of these are probably done aqueously, so while the calcite is submerged in water. And we do that to watch how the mineral dissolves or grows. So you'll notice on a lot of these pictures, especially C right there, it looks like there's steps. It's almost like a pyramid structure with steps. And what those are is the way minerals grow is typically by layer upon layer upon layer of single atom thick layers, right? And we call them steps. So this picture right on the right here is a rendering of what that kind of would look like on an atomic scale. You get these atoms lined up next to each other, and where they're going to dissolve or grow is going to be at the edges of those steps. So if you put a piece of calcite in the microscope, you just set it to scan picture after picture after picture. After an hour, you come back and you look at the first picture, and you look at the 30th picture, and those steps are going to move either forward, like in or out, depending if it's growing or dissolving. So that's one way that you can look at mineral growth and how it's growing and how it's dissolving. But I don't actually do it that way. I use this microscope in a completely different way. So So here's another picture of our tip of our probe that we put in our microscope. And so what I do is I actually don't scan or look at a picture of the mineral surface at all. I use what's known as resonance frequencies. And so the way we do that is every object, this table, me, my computer, a nail, anything, is just by virtue of having any kind of heat energy in it at all, and the material it's made of, it's going to have a vibrational frequency. Everything's vibrating in some way at some frequency, and that depends on a couple factors. It depends on the material it's made of. That is going to depend on the heat involved. That's going to depend on the weight, the density of that material. And what we can do is we can actually dunk this probe in water, and using that same technique, bouncing the laser off of the surface of the probe back to that photodiode, we can measure pretty accurately the frequency at which that probe is vibrating. And so here's the thing. If we're vibrating and then we start to grow crystals on that probe, it's going to get heavier. And what will happen is it's going to be vibrating like this, and then it'll start vibrating slower because it's harder to go back and forth if you have more weight on it, right? So we actually dunk this thing in water that's completely full of dissolved gypsum, and we wait for that gypsum to grow on our tip. And when it does, if we look at that in between those two black arrows, if we look at that frequency peak, right, that resonance peak, it should, if it's increasing in mass, shift to the left. So this is in kilohertz. So it should go from somewhere around, I don't know, 50 or 60 kilohertz down to maybe 40 or 50, right? Ballparking that number. But that's what we're looking for. And when that happens, that means that crystals have started growing on that tip. So what we do is the tip itself, the probe itself is fine. Minerals will grow on it. And in fact, this is a graph that we made from one of our early observations. So we put this tip in the water, we measured its vibrational frequency, and after about an hour and a half, we get this huge drop. So that initial rise there on the graph is probably just drift from heat. It's probably the temperatures changing inside the apparatus. That's going to change the vibrational frequency. But that huge drop, that is what we call nucleation. So that is when that crystal or that mineral goes from dissolved to a solid particle. And the time it takes for it to get from solution to start to nucleate is called the induction time. And that's what we're looking for in our research. This is most of the other graphs that we've gotten are not this pretty. This is the prettiest one we ever got, and it was like the first one we got. So I love this picture a lot. And so what we've started doing is that's all fine and good, but it's kind of annoying to take an hour and a half to wait for those crystals to grow. So what we've started doing is taking organic chemicals, these chains of organic molecules. One side of that organic chain is very attracted to gold, which is what our tip is plated in. So it's going to attach to that gold. And the other side is going to just be kind of a waving little chain of molecules out in the water waiting for something to come by. And it's particularly fond of calcium, which is the ion that gypsum is going to use to nucleate, right? So it's calcium sulfate. So we've coated our tips in these chemicals. Now when we put it in the water, instead of an hour and a half for induction time, we're getting something more along the lines of 10 to 15 minutes, which is really fast for a crystal. So what are we planning to do with this research? What's the application of it, right? So there are this technology called desalination. So desalination, as the name suggests, is taking water that has dissolved minerals in it, so ocean water, brackish water, right? And somehow getting that stuff out and purifying that water. There's a couple ways you can do that. One of which is through this little tube here called a desalination membrane. So there's lots of different applications for it. Most obvious of which is for drinking water, but it's also used for agriculture. If you've ever been on a cruise ship or a submarine, I've never been on a submarine, but if you have been, you probably were drinking water that was pushed through a desalination membrane. And how these things work is they're going to push this water through, and sometimes the membranes are porous, they have tiny little holes. Sometimes they're not porous, but they are permeable, so water molecules can still go through them. And the water is going to go through, Any of that other junk is going to be kept on one side, right? Just like that little animation there. So that's all well and good, but the problem with that is that once you start accumulating that material you don't want on the other side of the membrane, if you get enough of it, it's going to get oversaturated in that solution of water. And when that happens, it's going to start to crystallize. And it's going to start to do what's called mineral scaling. So you get all this mineral buildup on your desalination membrane. Makes it less efficient. Eventually, it's going to stop working. So eventually, you're going to have to swap it out for a new one or clean it. Now, salt, sodium chloride, that's easy enough to do, right? You just take this out, dunk it in some fresh water, dissolve the salt, put it back in. Things like gypsum, that's not so easy to do. And if you look at this little graph over here, everybody's probably heard typical standard water is going to be about 7 pH. That's not exactly true. It fluctuates. But for the most part, that's around where water is going to be. If we're getting pure water, which is what we hope to be pushing through, right? We could get calcium or calcite growing from the calcium ions in solution, but we're probably going to be in more of the 7 to 8 range in pH, and we're probably going to get gypsum crystallizing. So one of the things that we're hoping to do, but hoping to put data out there that's going to help other people construct these membranes, and we're hoping that we're going to have some data on different materials and whether or not different molecules are more or less resistant to mineral growth on them. So the different organic molecules we're putting on our probe, some of them might grow gypsum faster, some of them might grow gypsum slower. And if we can figure out some properties of different materials that can inhibit gypsum growth on these desalination membranes, they might get a little more efficient, and that would be much better for the technology because it's a very expensive technology. So other than small scale stuff like that, they're not typically cost effective, right? And so that is about it for my talk. And I will now take questions if you have them. And if not, that's okay. Yes. Mm. That's a good question. So they did at one point grow. So she was saying she was fascinated by the idea that rocks and minerals grow, that they'll grow over time. And she's asking, like, the rocks in Naaman's Creek that's right here, that flows through Arden, are those. So are you asking if they're still growing or if they have? Mm-hmm. Okay, so about the rocks in Naaman's Creek specifically, I can actually give you a really specific answer. So the general answer is sometimes. So So for the most part, what's going to happen to rocks when they're on the surface is they're going to erode. They're going to weather. So rather than growing, usually water is going to dissolve minerals and carry it away. There's something called frost wedging where little cracks in the rocks will get filled with water. In the wintertime, it freezes and it cracks the rock open and tiny particles are going to fall off. A lot of rocks, especially granitic rocks, are going to be made of a mineral called feldspar. And feldspar is particularly susceptible to water erosion. So it's actually going to dissolve and transform into clay materials. That's where clay comes from. So rocks are always changing. But yes, sometimes, so if you go out west, and some of the rocks I think around here will do this too, you can get oxidation on the outside of rocks. So just like iron rusts, the iron and magnesium and calcium and things in the rocks can also rust. And sometimes you'll get patinas or veneers over top of rocks. If you go out west, it's called desert varnish. And actually a lot of the petroglyphs that you see out west, so like Native American people drawing pictures and glyphs in the rocks, those are done in desert varnish. Those are done on the oxide layers on the outside of rocks. So yes, they do grow. The rocks in Naaman's Creek are, so I do know the story behind those and how they got there. So we live in the Appalachian Piedmont. So we live at the very, very foothills of the Appalachian Mountains. And these mountains, the Appalachians are some of the oldest mountains in the world. They are about 430 million years old. specifically the rocks here in Delaware. And so the rocks that you find in Naaman's Creek are part of the Wilmington complex. And so these rocks at one point were a volcanic island arc. So I don't think quite as big as like something like Japan, but like quite a large arc of volcanic islands that as the plates were moving around, ancient North America's over here, volcanic islands arcs over here, it slams into North America. And when two plates come together, unless they subduct, even when they subduct, they make mountain ranges. So all that pressure is going to push up those rocks. And so the rocks we have here in Delaware are volcanic rocks that got smushed and metamorphosed into different rocks called gneisses. And they got pushed underground probably several miles. I don't know the exact depth, but they were very, very deep underground. And only after uplift and erosion have they come back to the surface again. And now we can find them here. So at one point, they were volcanic rocks on an island, and now they're not. So yeah, now they're Naaman's Creek. Yeah. Yep. Yeah, good question. They're getting smaller. Yeah, the ones around here are getting smaller. Yeah. Yes. Ooh, that's a good question. Sorry. So she said, were any of them brought here by glaciers? So I don't believe so. I believe where Delaware is was below where the last glacial maximum was. So the last glacial maximum, if you go up to New York City, the rocks in Central Park, those are glacier smooth rocks. So actually there's grooves. Yeah, there's grooves in the rocks in Central Park, and those are from pebbles at the bottom of glaciers being dragged across the rocks for like thousands of years. So those were exposed to glaciers. I don't believe the ones here are glacier material, no. Yeah, good question though. Yeah. Is that, no, okay. All right, yeah. Calvert Cliffs. Yep, yes. Yes, I have. Yeah, so Calvert Cliffs is awesome. So that's Miocene, I think. So we're talking like 20 million years. That's off the top of my head. I don't know if that's something like that. Yeah. So you can supposedly you can find megalodon teeth there. I never have, but yeah, there is. Yeah, it's a great hike. Really nice hike down to the beach, and you can see some beautiful cliff faces. Yeah. Yeah. Yes. Masters. Yeah. Oh. Yeah, that's a good question. So he asked if we've noticed in the university if there's an increase in geology students or people interested in geology. Um, the sad answer to that is no, but it's not because people aren't interested in geology. It's because pretty much any university this is the case, the COVID really affected our enrollment numbers. And so one of the ways we got a lot of students was through people who took elective classes. And then realized like, oh man, this is actually really, really neat. I want to switch to that major. And over COVID, that wasn't really happening. So our numbers actually went way, way down, and we are starting to build them back up, but we're not where we were pre-COVID. Yeah. So I don't think it has anything to do with people not being interested in geology. It's just the product of the times. Hmm. Yeah. I hear what you're saying. Yeah, so I know one thing I can definitely tell you is that one area of study that a lot of people are doing around here, that we have several master's students, I believe we have a few that do this, is offshore wind. So yeah, so that's an area that is really in Europe it's huge. So they have a ton of offshore wind farms there. We have like two here in the U.S., but we just leased a bunch of or we're I don't know if the leasing is finished, but they were doing bidding on a bunch of leases for offshore wind farms in the United States. And yeah, no. Oh, is that okay? So well, then okay. So apparently not with Trump. That's unfortunate. But I do know that it's an area of study for a lot of people. So yeah, so you need geologists to to look at the subsurface of the ocean and the rocks that are there to see if that's a suitable place to put these wind turbines. So that's one of the areas of study. Yeah. Oh, geothermal. Mm-hmm. Sure. For sure. Yeah. I'll admit that this is not a topic I'm super well versed in. I only know the bare basics. But yeah, geothermal. So it's you have to have a place that has a high geothermal gradient to do that efficiently. So somewhere, so we were talking about Iceland earlier. Yeah, Iceland is a place that's almost 100% geothermal, as far as I know. Um, mm, yeah. So the Mariana Trench is mostly, well, most of that depth is water, so it's still the same distance to drill through that rock to get to the. I don't know. That I honestly don't know the answer to that question. It would be easier or harder down there. Yeah, that's a great question. Yeah. Yes. Oh, really? Oh. Oh, yeah. Yes. Yeah. So he was asking, and you said in Montana. In Montana, they found lithium in the groundwater. I know nothing about that, but that's really so they were trying to get it out, and well, so that is a valuable natural resource. Absolutely, is lithium mining. Yeah. So I think a lot of it is it Afghanistan that a lot of it comes out of right now. I mean, I think it might be. Yeah. So if we could get it out of the groundwater, that would be a big deal. If we could get it out efficiently, where we could actually use it. Yeah. Yeah. No, exactly right. Exactly right. Yeah. Crystallize it out of the water. Let's do over here and then yes. Yeah. Mm. Mm. Y- Yeah. Ooh, that's a really good question. So he's asking about the volcanic island arc I talked about that slammed into North America. And so you asked when that happened and if there was a name. I don't know if there was a name of the island arc. I do know that what is now North America was known as Laurentia back then, was the proto-continent name for it. And that happened around, the exact age is foggy in my mind, but it was somewhere around 400 to 430 million years ago is when that happened. Yeah. So yeah, the rocks we have here in Delaware are quite old, which is really cool. Yeah. Yes. Sure. Hmm. Yeah. So she's asking about Yellowstone, and is it a huge area for geothermal heat? Absolutely. I mean, I don't know off the top of my head any specifics, but that is definitely an area where the geothermal gradient would be very high. So I mean, you have hot springs and things like that in that area. So yeah. So Yellowstone is over top of what's known as a mantle plume. So it's a hot spot. So there's hot rock and magma coming from the deep mantle. Possibly some mantle plumes can come from close to the core, is where they originate, and comes up, and that hot rock really pushes through the crust. And we're not talking like it's not like the magma's like 10 feet below your feet or anything in Yellowstone, but it's pretty close to the surface, so you get a lot of heat from that. Yeah. So Hawaii is another place where that happens. That's on a geothermal hotspot as well. Yeah, so those are places where you could get a lot of geothermal energy from. I don't know anything about the specifics in Yellowstone, but I bet they do. Yeah, it's a good question. Yeah. All right. Well, I'll be up here if you have any more questions, and please feel free to come up and check out the rocks that I brought if you'd like. So thank you all very much.